Can you hear me? Excellent. So let me remind you of our discussion yesterday. We said that we started the lectures by saying there were contexts in which something like ADS-CFT happens at the classical level. And that something like ADS-CFT happening at the classical level was basically the statement that the classical equations of gravity under certain situations reduce to non-gravitational equations. In yesterday's lecture, I reviewed the best understood context in which this happens. This was the so-called fluid-gravity duality. We looked at gravity with a negative cosmological constant in asymptotic ADS spaces. We focused on a certain long wavelength limit of the gravity equations. A limit in which the variation in field theory directions was at much larger length scales than the temperature set, the local value of the temperature of the local Bragg grains that we were perturbing around. Okay? And we found that in that context, the equations of gravity is the equation of hydrodynamics. So gravity went to the equation del mu T mu nu is equal to 0, where T mu nu was a specific expression built out of temperature, local temperatures and local velocities. The expression of a T mu nu as function of local temperatures and velocities for constitutive relations. The constitutive relations for the fluid that we were studying was determined by gravity. It's a very special kind of constitutive relation because it comes out of Einstein's equation. It's the constitutive relation of n equals 4 Young's theory at large. Strong coupling. So it's a constitutive relation also if you many other theories. Any theory whose bulk dual description admits a consistent truncation to Einstein's equation for the negative cosmological constant. There are plenty of such theories. So some are very special constitutive relations. We talked a little bit about the utility of this. Okay. In today's lectures, we're going to move to studying a second situation, okay, in which the equations of gravity reduce to non-gravitational equations. Once again, the situation that we will study will involve black holes and event horizons. Okay? However, we will not have negative cosmological constant, or not necessarily have negative cosmological constant in what we're doing. Much of what I'm saying has easy generalizations to situations with cosmological constants. But it's not needed, and so we'll turn it off in the introductory part, in the first part of these lectures. Okay? What we're going to be doing then is to study the dynamics of black holes, just in flat space. The kind of black holes that participate in the LIGO collision. Unfortunately, as you will see, we'll be able to make progress not for black holes in 4 dimensions, but only for black holes in a large number of dimensions. So, what we do will hopefully be useful for a large D version of the LIGO experiment. Okay. Okay. So to start our discussion, let me review what the black hole solution in flat space. So the black hole solution in flat space in d space-time dimensions is minus dt squared to 1 minus r0 divided by r to the power minus 3 plus dr squared over 1 minus r0 by r to the power minus 3 plus r squared d omega d minus 2 squared. This is a simple generalization of the Schwarzschild black hole in 4 dimensions. Schwarzschild worked in 4 dimensions and this power was 1. The general solution is the same, except that the power gets replaced by d minus 3. And this is related to the fact that the equation del square phi is equal to 0 has a solution that goes like 1 over r to the power d minus 3 in d minus 3, the Euclidean sections. You know, the Coulomb law in 4 dimensions is 1 over r, Coulomb law or Newton law in d dimensions would be 1 over r to the power d minus 3. Okay. Now, to start this discussion, I'm going to make some simple observations about this black hole solution. These observations are trivial, but they're interesting. And these observations were first made by Emkaram, Suzuki, and Tanami. Okay? And the observations go as follows. The first observation is this. Suppose I take R to be larger than R0. Maybe R is equal to twice. Okay? And I hold the ratio R0 by R fixed as I take d goes to infinity. So let's say R is equal to twice R0, so R0 by R is half. I keep half fixed and I take the limit d goes to infinity. Question, what happens to this metric? Okay? So the values of R in which I'm focusing, the answer is obvious. Because you see this quantity R0 by R, which is the quantity that makes this metric differ from the flat space metric. R0 by R to the power d minus 3 would be like half to the power d minus 3. But half to the power d minus 3, the limit d goes to infinity, is 0. Okay? In fact, it very rapidly goes to 0. Okay? So, this quantity here, if we do this, we hold R greater than R0 and keep R0 by R fixed as I take d goes to infinity, the metric goes to flat space. This is obvious. Okay? Physically what's going on? Physically what's going on is that the Newton law has a very fast fall off in the electrons. Okay, so if you've got Newtonian potential non-trivial at R0, you go to twice R0, you've got almost 0. Okay? Twice, this could be replaced by 1.1 or 1.01, any number that's larger than 1 that goes to, let's say, fixed as d goes to infinity. What does this mean? It means that we're a large number of dimensions and we stay a fixed distance away from the event horizon, take the limit d goes to infinity, we don't see that there's a black hole. That's already interesting. Now, let's try to make the statement a little more fine-grained. You see, if we're at R equals R0, we're on the event horizon of this black hole. And surely we see it as a black hole, because event horizons are causal boundless in every dimension. So in particular, the limit d goes to infinity. So when we're away from R equals R0, we don't see it, so there must be some distance scale over which we start seeing it. Let's figure out what that distance scale is. Okay? Suppose we take R is equal to R0 into 1 plus alpha by d. Okay? And suppose I hold alpha fixed as I take d to infinity. Then let's look at what happens to this quantity R0 by R to the power d minus 3. Let me put d minus 3 here. Makes very little difference because d is very large. But cleanliness, d minus 3. Okay? So this quantity R0 by R to the power d minus 3 is equal to 1 over 1 plus alpha by d minus 3 to the power d minus 3. Okay? But d is going to infinity. And so, a famous limit tells you that this is e to the power minus alpha. Back when I was in school, this is how e was defined for me. E was defined by this limit. Okay? So, what does this tell us? This tells us, you see, if I held alpha fixed as I take d to infinity, what am I doing physically? What I'm doing physically is, as I take d to infinity, I'm restricting attention to points that are at a distance 1 over d away from the event horizon. And when I do that, I take d to infinity and simultaneously scale towards the event horizon, so that I'm always a distance 1 over d away from the event horizon. I start seeing the black hole. Because then this picks up the deviation of this metric from flat space is none. Is this clear? This first observation, which is basically trivial, but still interesting, is an observation of their word in the following language. Black holes have a thickness. And by the thickness of the black hole, I mean the distance that you have to move away from the event horizon, after which you essentially are blind to the existence of the black hole. You were basically in flat space. Okay? You can check that the effect of the black hole decays exponentially over this length scale. So that's a clear sense in which we have a thickness of the black hole. Is this clear? Yes?
Would this have anything to do with the stretched horizon?
Yeah, as we're going to see, all of the physics in this region will be summarized by an effective equation for movement. Yes. So in some sense, yeah, the idea of the stretch horizon was to look at a surface a little bit away from the event horizon. Here what we're going to do, as you will see as the lecture's gone, is summarize the physics of this whole region. So not a particular slice, but the whole region, into a lower dimensional equation of motion. And we're going to do it because this region's so thin. Okay, excellent, but excellent question. Other questions on it? Excellent. Now, you see, this thickness of the black hole has dynamical significance. And in order to understand the dynamical significance, I'm going to now take you through a calculation, or the results of a calculation of the quasi-normal mode spectrum of black holes as a function of d when d is large. So we talked about the quasi-normal mode spectrum of black brains in ADS. I'm now going to define what I mean by quasi-normal modes of black holes in flat space. So I've got a black hole here. So it's a particular solution to the equations of motion. And I take Einstein's equations and I linearize it around the solution. Okay? As always, I'm interested in this linearized problem with some boundary conditions. So the boundary conditions are at two places. The first one's at the event horizon, at which we demand that everything's ingoing, very much like the ADS. The new thing here is infinity. And when we were studying the ADS problem, we had a very natural boundary condition at infinity. We just demanded normalizability from the point of view of the quantum field. Here, we've got at infinity because the infinity of flat space. We don't have a notion of normalizability. What boundary conditions should be imposed at infinity? Let me first tell you what boundary conditions are imposed, and then I'll tell you why. The boundary conditions that are imposed is that the solution is purely outgoing at infinity. Or more precisely, that the ingoing part of the solution at infinity vanishes. Alright. So at the mathematical level, these are some boundary conditions. Okay? There's boundary condition ingoing to the event horizon and outgoing at infinity, and who can argue with, if you want to study these boundary conditions, who can argue with you? But of course, the reason that you study the problem of these boundary conditions is that these boundary conditions have some physical significance. So let's try to understand what the physical significance of these boundary conditions. Imagine the following experiment. Imagine you have a black hole and you hit the black hole. Perhaps you take an asteroid and you hurl it into the black hole. Okay? So you said, but asteroids are thought to be a model theoretically, so let's say you take a lump of scalar field and you hurl that into the black hole. Okay. Or maybe a lump of gravitons and hurl that into the black hole. Okay. Now, you hurl the stuff into the black hole, hit the black hole, and then you stop hitting it. Now what do you expect? The black hole is going to settle down. Because black hole physics is dissipative. You forced it to go away from its equilibrium state. The black hole is going to go back to its equilibrium state in a certain way. The question of how the black hole goes back into its equilibrium state after you hit it is an interesting question. Okay? How it happens at a nonlinear level, well, we're going to understand it largely. But in general, it's very tough. But at linearized order, that should be an easy problem. It should be a matter of solving Einstein's equations linearized around the black hole solution. But we've got boundary conditions. Well, what is hitting the black hole from the point of view of the scalar field or from the point of view of gravitons? Hitting the black hole, as we've seen, is throwing something into the black hole. The point is that we want to understand what happens to the black hole after we've stopped hitting it. So we've stopped throwing stuff into it. Okay? Which means there should be no ingoing stuff. So if you want a basis of modes in which you can expand what happens to the black hole after it stops being hit, the boundary conditions that you should impose at infinity are that there's nothing ingoing in it. Okay? So this quasi-normal mode problem, which is a problem that general relativists love, answers the question: what are the modes in which you can expand to answer the question at linearized order? What happens to the black hole after you stop it? How does it settle back into its place? Yes, sir?
Are those will they be a complete set of states?
No, actually they're not a complete set of states.
They're like bound states on the surface?
Yeah, the operator for which these these states are diagonalized, not a Hermitian operator. Okay, because the boundary conditions make this not Hermitian. And I think there is a sense in which length time behavior can asymptotically always be expanded in these modes, but it's not, you know, a complete set of states in any strict sense. Yeah, and that's an interesting question. Yeah. Okay. Excellent. So now the next question that we want to address is these quasi-normal modes. How do we describe them? Well, in the ADS context, we use the translation invariance of the ADS brain to put all the modes, take all the modes and make them into the pi k dot x. In our context now, we don't have translation invariance, but we've got something that's as good, that's better, which is rotation invariance. So what we're going to do is to take all modes and expand them in spherical harmonics. Okay, tensor, vector, and scalar spherical harmonics, depending on which components of the metric we deal. Okay? So, schematically what we'll do is to take the modes and some modes. To make the equations precise, I need to put a lot of indices, so I won't do that. What's needed. Some spherical harmonic times e to the power I omega t. Now, because of rotational invariance, we can work spherical harmonic by spherical harmonic. Okay, we can work the particular L sector, L sector. And then try to solve the problem, Now we get an ordinary differential equation because we dealt with the angular effects. The ordinary differential equation is an equation in R. Okay? So we get an ordinary differential equation, and once again now we have a particle in a box. Like we had in ADS. Okay? Particle in a one-dimensional box. Once again what we should expect is a bunch of discrete modes labeled by some parameter n, which tells you how many times the wave function wiggles between where you want to go. However, if you think about it, it's confusing at the beginning. You might at first think that this box is infinite length. Because unlike in ADS, in flat space, the distance to infinity dynamically is infinite. However, when you work out this problem, or if you think about it a little more, you see that this infinite length here is a bit fake. And the reason for that is the following. Suppose we've got the black hole, and there's a certain distance after which the metric of the black hole reduces to flat space. Then, putting the boundary condition infinity here is as good as putting some other boundary condition here, which is the boundary condition of, if I were to propagate in flat space, I would end up with outgoing at infinity. So the non-trivial part of the boundary condition can effectively be imposed at the first place where the solution starts deviating, where we cannot distinguish the solution from flat space. Okay? So, the non-trivial part of the boundary condition can effectively be imposed at R is equal to R naught plus R naught by D times some numbers, let's say 100. We get parametric dependence. Is this clear? Because we just argued that this place, this thickness of the black hole is R naught by D. Is this clear? Great. The size of the box is R naught by D. Right? Because one boundary condition is imposed at R naught, and the other one is R naught plus R naught by D. Okay? So it's an interval of size R naught by D. Effective. Okay, now we've got this box which is really a shell, right? Because there's the sphere. Okay, we've dealt with the sphere in our mind for spherical harmonics, but physically it's a shell. And we've got the outside of the box and the inside of the box, and we've got effective boundary conditions of these two places. So now I suppose what we're doing is solving some wave equation in this region. So suppose we wanted to solve a wave equation in such a shell. Einstein's equation is complicated, but if we were doing something a bit more simple, let's say del square phi is okay, you've got some wave equation here. What would you expect? Well, of course you would expand in spherical harmonics like we've done. And you would expect to look at solutions with certain number of wiggles between one end and the other of the shell. So you would expect that the modes will have omega that schematically goes like n divided by R naught by D. Number of wiggles between inner and outer. Okay, plus L divided by R naught. number of wheels in this way, in this sense. Yes?
Does the box have to be big enough so that the black hole can because if the box is too small?
You know, we're just solving a classical wave equation. We're doing nothing. Okay, there's no thermal equilibrium, no Hawking radiation. Okay, maybe there's a question when you think deeply, but at the moment, I'm just being pedestrian. Okay? Is this clear? This is what you could schematically expect. Now, the important thing about this formula is that this is much larger than this. So this is n times d divided by r, plus L divided by r. Okay? So, unless there was a mode in which this effective n was 0, all other modes would have frequencies of order 1 of d divided by r. Okay? D is very big, what we're doing. Please make heavy frequencies. By the way, these frequencies will not be real, they will have imaginary parts that represent decay. And the frequencies of order d divided by r will be both the real part and the imaginary part will represent very rapid decay. Okay, so very rapid return to equilibrium along these continuums. Okay? Now the interesting question is, are there special modes such that this term vanishes? Sort of zero modes in the radial direction. Do they exist such modes? This requires a calculation, or I'll give you arguments, more or less arguments, as we go along with our calculation. But at least historically it's first discovered by calculation. You do a calculation, I won't tell you how. But okay, you do a calculation and you find the answer is yes. In the scalar and vector sector, at every L, there are 2 modes. In the scalar sector, and in the vector sector, at every L, is 1. These modes are like in the sense that their frequencies go like 1 by r naught, or like L by r naught. Okay? Every other one of the infinite number of modes of the problem has frequencies that go like d by r naught. Okay? So now there's hope for a place where things will become simple. Because we've got a separation of scales. What's the separation of scales? The separation of scales is between the length of the wavelength that can fit in our box, which is r naught, and the thickness of the black hole, which is setting the length scale or mass scale for generic quasi-normal mode frequencies, which is d by r. Okay? The box is much bigger than d by r naught. So if we work in a region, so look at ripples of the black hole whose size is arbitrary, but not of order 1 by d. Okay? For those problems, you would imagine that the light modes, namely these modes, are the only important modes of the problem. You would imagine that there is a sense in which you can integrate out the heavy modes to make a theory of the light modes. This is exactly how it works in fluid gravity correspondence, as we reviewed last time. And it's going to work in the same way here. Okay? So for the rest of our lectures, this is our goal. Our goal is to find the effective theory of light modes that will govern black hole dynamics on length scales that are much, much larger than r naught by d, but of course smaller than r naught, because there's no scale. Is this clear? Is the goal clear? Questions or comments? They don't depend on K, on L you mean? What is K? Momentum. Yeah, so you see, we're now in a sphere. So there's no linear K. The thing that replaces K is L. It's the angular weight. So they do depend on L in a manner that we will understand as we go. Okay? I'm going to at some point derive the frequency of these modes, but from a more sophisticated function. But they will depend on L. Okay, other questions, comments? Excellent. So, what we now want to do is to look at the effective theory of these light modes. But in order to do that, I need to do some irritating preparatory work. Okay? So we're going to take a 15-minute diversion for irritating but necessary preparatory activity. Okay, sorry. Okay. There are various sort of small preparatory things I have to do. The first is, how do we count powers of D? This seems like a strange question until you think about it. The point of this question is as follows. You see, I want to make what is effectively a long wavelength expansion. On length scale, compared to the scale, R naught divided by D. Okay? But this long wavelength expansion is effectively an expansion in 1 over D. Because the longest wavelength in our problem is R naught. So, effectively the ratios of the length scales that we are interested in the problem, dynamical length scales divided by the small length scale is effectively D. So the small parameter is effectively 1. However, D does not play only a role of setting this length scale. It has another manifest role, the dimensionality of the space-time in which we live. Okay? So, the small parameter in our problem is 1 over D, but we may get powers from two different sources. A, from length scales, and B, because there are lots of dimensions. It will turn out that everything is simple only in the limit in which we don't get powers of D from the second thing. Okay? Now, how do I make that happen? So there is one clean context in which this is true, though I'm going to state a clean context in which what I'm saying will work, though there are many other contexts in which it also works. But it's usually in this clean context. Suppose we restrict in our mind attention, we restrict to situations that preserve and SOD minus P minus 2 isometry. Okay? So we're going to, where P is held fixed as D is taken to infinity. Suppose we restrict our attention to such situations. Okay? We will count powers of D, assuming this is true. Then everything that we say will work whenever our D counting works, whether or not this is true. But this will be our rule for counting powers of D. So let me make one or two quick comments. Okay, first let me do the counting and then I'll make a couple of quick comments about this restriction. Okay? First let's just do the algebra, then let me try to understand why this is the reason for doing it. Okay. So suppose I have such a situation, I've got a rotational SOD minus P minus 2 isometric. So in such a situation, I could always work in a metric, such that the coordinates in which the flat space metric takes the form minus dt squared plus dr squared plus dr squared d omega d minus p minus 1 squared plus dxi squared, where I is equal to 1 to, I think, p plus 1. P minus 2, sorry. Okay? So what am I doing? I'm looking at space-time. I'm dividing it up into I'm looking at flat space, and I'm dividing it up into d minus p minus 2 directions and p plus 2 directions. Okay? The p plus 2 directions are these p plus 1 and time. And the d minus p minus 2 directions are these directions. And I'm going to restrict to configurations that preserve rotational invariance in the d minus p minus 2 directions. Because I'm interested in things that preserve rotational invariance in that direction, it's convenient to go to polar coordinates in that factor of my space-time. Is this clear? Is this clear? Was this confusing? Okay? So, if I look at things that depend only on xi, t and r, then that manifestly preserves my S of d minus p minus 2 isolation. Okay? So now, just to train ourselves, let's suppose I've got a function phi. And this function phi is a function of t, it preserves the isometry, so it's a function of t, r, and xi. Okay? I'm going to assume that my function phi always varies on length scale 1. So the d never enters this explicit function as a function of t, r, and xi. Okay? So all of the variation is smooth, plus it preserves this isometry. In this situation, question, what is del mu phi, del mu phi? What is the order in d of del mu phi, del mu phi? Obviously, this is order 1. Because you can write an explicit formula for it. It's a sum over order p terms. P doesn't have any d in it. Each term is independent of d, so it's order 1. And it's an obvious statement. I make the statement, contrast it with the following other statement. If you look at the quantity del squared phi, let's evaluate this quantity. This quantity has a piece that is clearly order 1, which is del I phi. Another piece that's clearly order 1, which is del p squared phi. But then it has contributions from this part. From this part, we work in polar coordinates. So we get plus 1 over r to the power d minus p minus 3 del r to the power d minus p minus 3 del r on phi. Is this clear? Right? It's a trivial writing of del square in part planar, part polar coordinates. Yes?
You also have the other t minus.
Yes, we also have the other. Sorry, no, we don't, because nothing depends on the angles.
With the xi one?
Sorry?
The p minus 1.
That's this. Right? So we've got these and these. These don't matter because whatever they are, they're order 1. Okay? This though has an explicit d in it. So, where does the explicit d come from? It comes when you add this guy and this. So, to leading order, this guy is 1 by, this guy is 1 by r d minus p minus 3 times del r of phi. Since del r of phi is generically order 1, this guy is generically order. So you see, in such a situation, del phi, the whole thing squared is order 1, but del squared phi is order 2. Del phi, whole thing squared, and del squared phi both have 2 derivations. But they behave differently in decount. Okay? This is something we'll have to be careful of all through our analysis. For instance, when we deal with vector fields, a generic vector will have am equals order 1. But del m, same kind of reasoning. You write the formula for del m using the formula involving square root g's, you know what I mean? And we'll say that this is order 2. Okay? So when you get derivatives of quantities, we will always estimate the d-dependence. We will always estimate the d-dependence by assuming that we have an SOD minus P minus SOD minus P minus 2 isometry. Okay? Everything I say from now on, will not make any assumption about the nature of the SO B minus 2 isometric. Will work for any particular choice of P that is held fixed as the most infinite. And in fact, will work in a much wider class of situations. Because all I will use this isometry assumption for is to estimate powers of D. And you can engineer much larger classes of situations than this explicit isometry that obey this D coupling. Nonetheless, restricting two situations with this isometry is anyway quite interesting. For instance, suppose we were interested in calculating what happens when a black hole collides another black hole head on in D dimension. That situation obviously has an SO D minus 2 isometry. Because two directions are special, the direction around which the black holes are approaching, and time. So that would be the case P equals 0. Okay? If the black holes were offset in one direction, it would have an SO D minus 3 isometry. Okay? So many interesting physical situations in which such an isometry exists. What I'm going to say will apply to every such situation, and more generally, but whenever we are confused about counting powers of D, we will assume this isometry, go back and use that count. Okay? This is basically, okay, the last physical comment about this is the following. You see, the kind of thing that our approximations will not be able to capture is the kind of thing that happens when you're trying to probe a solution that exists only because D is very large. A solution in which some energy goes here, some energy goes there, some energy goes there, and splits up in all the D directions. Now, such solutions don't have a clean large D limit because the nature of the solution depends on having a lot of space to go in. Okay? So making such an isometric assumption makes it clear that we're dealing with solutions that have an analog at every value of D that is large enough. Okay. So with what follows, we're going to make this assumption and proceed that powers of D in derivatives are counting assuming there's an isometry, even though, as I said, I'll give you examples. There are more general situations in which this power counting works. Okay. Whenever this power counting is correct, what I'm going to say works. Okay. Questions, comments on this? Okay, so this was the first irritating technicality. There's a second irritating technicality that I have to deal with. Okay, and well, it's not so irritating, it's quite nice. The second nice technicality. And that is the following. I am going to need, in what follows, to solve the following equation. More generally, as we proceed, we will need to solve a sort of auxiliary problem. Okay, but first let me deal with this. I'm going to need to solve this equation subject to two boundary conditions. Rho is equal to 1 on a given surface in space-time. Some codimension 1. And rho is purely outgoing at infinity. It's some reasonable boundary condition. Okay? The surface I have in mind is some sort of tubular region. You should think of it as the world volume of a codimension 1 membrane. Okay? So I'm going to try to solve this equation del square phi is equal to 1 over rho to the power d minus 3. I'm going to solve it as a function of the shape of the straight surface on which the boundary condition 1 is imposed. Now, this is just a linear equation. It looks non-linear because I've written it as rho to the power d minus 3. If I make the field redefinition, phi is equal to 1 over rho to the power d minus 3. It's a linear equation. But you know, it's an equation that you could, in principle, solve. But in a finite number of dimensions, the solution, suppose I was here, would depend in a very complicated way on the nature of the surface area. What we're going to see now is that in the large D limit in a Taylor expansion around around this surface here, build rho in a completely local way. So the Taylor expansion will not need to know, if I want to know what rho is just a little bit away from the surface, I will not need to know the nature of the surface everywhere. I only need to know the nature of the surface nearby. Okay? This is actually not true in general. It's actually not true in general at finite values of p, but it is true at large. Okay? I'm going to now show you why this is true. So let me quickly go through the algebra. Okay? Let me quickly go through the algebra. See, suppose I'm interested in solving this equation. I just open it out. Okay? I'm going to look for a function rho that varies of length scale unit. So I just take that equation and open it up. So you see, when I take one del, I get del rho by rho to the power d minus 2. And then when I take the second del, I can either act again on this rho to the power d minus 2, or I can act on the del. If I act on the del rho, I'll get del squared rho to the power d minus, with the coefficient d minus 3, divided by rho to the power d minus 2. Right? That's when I act both dels on the same row. On the other hand, if I act both dels on different rows, what I'll get is, and I've got a minus sign here, I get a plus d minus 3 into d minus 2 into del rho the whole thing squared divided by rho to the power d minus 1. This is supposed to be equal to 0, so this whole thing is 0. Okay? Which implies that rho del squared rho minus del squared rho is equal to d minus 2 del rho the whole thing squared. This equation is true everywhere, and I'm going to study this equation evaluated on the special surface where I put the boundary condition rho is equal to 1. Okay? I'm going to study this equation on the special surface where I put the boundary condition rho is equal to 1. This quantity here, this del square rho, okay, is completely determined to leading order in the large D expansion by the nature of the surface rho equals 1. This is because you see D, this quantity, see, you might have first thought this is order D, but this is order 1. But that's not true, because remember, the del square should be counted as order D. So this quantity is order D, but it's only counted as order D because you get, if you preserve your isometric, a factor, a derivative along the radius of the large sphere. Okay? So you can break up this del square as acting in the normal directions and in the world body directions. Okay? Almost all of the large sphere is in the world body directions. Just some order 1 part is not. Okay? So all of the order D part of this comes entirely by knowing the shape of the surface. The derivatives of the surface only contribute to order 1. So if you know what the surface is doing, you know this quantity. But that tells you know what del rho is. But you see, I knew rho was equal to 1 on the surface. And I know del rho. So I know what rho is a little bit away from the surface. Because del rho is the vector that tells you how to go from a point on the surface to a point a little bit away. Okay? And you can systematically carry this out order by order, 1 by d. Let me give you, I'm sorry for this, we're going to need it. Let me give you the answer in a nice form. You can show that rho is equal to 1 plus s of x mu into k by d minus 2 plus 2 by k del hat squared 1 by 2. Del hat squared of something else. So what are all these quantities? Suppose I've got my surface here. Given any, and I've got a little point away from the surface. What I do is I take this point and I draw a normal from the surface that hits this point. Order by order in an expansion in distances away from the surface, this can be done uniquely. You might have caustics if you go too far away. But we don't. We just take data. Okay? So associated with any point x, there is a point x hat on the bound, on my surface. S of x is the distance from my point to the membrane along this norm. And k is the trace of the extrinsic curvature at the point x hat. Okay? Del hat squared is the derivative along the bound. I think I can find everything. In actual calculations, we use formulas like this. I'm not going to trouble you with such formulas very much after this one, just to show you that you can do things explicitly. Okay? So, basically what I've claimed is that you can construct rho order by order and distance away from the membrane, entirely in terms of local data of the shape of the membrane where you are. Is this clear? Please.
From that equation, you only know the magnitude of grad rho.
You only know the magnitude of grad rho, but grad rho is normal to your surface. You know your surface. Yes, exactly. So at the moment we're just doing first expansion away from the membrane. Okay? Then you have to reiterate this. You have to keep going. But you see, knowing that the magnitude of grad rho is enough because you know the surface. Okay, yeah. Sorry? There shouldn't be any, so wait, tell me when.
Oh, no, 1 over 2. What is that?
That's K.
No, next. Right next to it.
That's K.
Okay.
Sorry. Other questions or comments? Okay, the details of this one, we have worked out the second order term, we needed to do something. Okay, and you can go on forever. The important point is that you always generate what's going on in terms of local data around the surface. Okay? So this problem of solving, you see why this is so unintuitive. There are two things about this that's unintuitive. The first is that although I specified a problem for what K is for you, in terms of boundary conditions on the membrane and boundary conditions at infinity, in order to solve it, I never used the boundary condition at infinity. That sounds strange, it almost sounds wrong. Because the solution should be characterized by two boundary conditions. Okay? Hold that thought, we'll come clear it up. Okay, we'll clear it up very soon. Okay. Now, there's one more irritating algebraic thing I have to do, but I'll do it when we need it. Because we get too many. Okay, so now let's get back to physics. Okay? Could I take maybe 5 minutes more? 10 minutes. Okay. So, no, I'll take 15 minutes. Plus minus. Okay. So now we're going to get back to physics. You see, with this, what we wanted to do was to try to find the nonlinear theory of the light modes that describe non-linear black hole motion in flat space, but over distant scales that have no one over the net. Okay? How are we going to do this? Well, steps that we used when we were studying fluid gravity. We did many things, but one thing that was important when studying fluid gravity is find the right coordinate system. See, this is a dirty secret of physics. When you first study general relativity or gauge theory, all the textbooks make a big deal of telling you that the coordinate system doesn't matter. And that's true in principle. It's one of these things that's true in principle but untrue in practice. The coordinate system is everything when you want to solve a problem. You know, a problem that is, for instance, you know the right definition of Kruskal coordinates is? It's the coordinates that are useless for every calculation. Okay, so, you know, things may in principle work out like a coordinate system, but getting the coordinate system right is the difference between being able to solve a problem and not. Okay? So I want to work on the right coordinate system, and the first thing I'm going to do is use what we had from what we knew from you know, our intuition from fluid gravity to try to take this black hole and move to ingoing Eddington Finkelstein coordinates. Okay, that's nice because as we saw in fluid gravity, it makes the horizon regular, manifestly regular. And that's sort of nice. We're going to have to do one more step, but first let's do that step. So we had dr squared is equal to minus dt squared into 1 minus r naught by r to the power d minus 3 plus dr squared over 1 minus r naught by r to the power d minus 3 plus r squared into omega squared. Now we've got ingoing Eddington Finkelstein coordinates in a radial manner. By which I mean, we'll call this whole thing like last time f of r, and we'll make the coordinate change. V is equal to t plus integral dr f of r. Okay? So V is equal to t plus integral dr f of r. If you do it, just follow the same algebra as last time. You will find dr squared is equal to 2 dr dv minus dv squared into, let's just call it f. Okay, let's keep it. 1 minus r naught by r to the power d plus 3 plus d r squared d omega squared. Okay, this is just a repeat what we did last time. Now, you see, in Eddington Finkelstein coordinates is very convenient when we're studying fluid gravity because it mixed V with R, where R was a coordinate orthogonal to the coordinates that had all the symmetries of our problem. All the interesting symmetries of our problem at finite temperature lived in the field theory directions. For instance, translation directions, field theory directions. And we mixed with the coordinate R that had nothing to do with translations in the field theory directions. However, when we're studying black hole motion, this is a very unnatural thing. Because you see, when we're studying black holes moving, and as we study a black hole moving, R will become an unnatural coordinate. Let's say we have two black holes. Are we going to use R based on the center of the first or the second? Okay, this is clearly an unnatural thing to do because it obscures the symmetry of flat space. So what we've got here is a coordinate system which maintains the regularity of the event horizon, but is somehow unpleasant. Okay? It's unpleasant all the way. You know, this, for instance, at r equals infinity, this coordinate system describes flat space, but it's not immediately obvious to the naked eye that it's flat space. You have to do a coordinate change to see it. Okay? Now what we're going to do is to make another coordinate change that at least at infinity undoes this unpleasant feature. You'll see. Okay? What we're going to do is to undo this coordinate change but only at infinity. By which I mean we're going to define V is equal to T, we'll call it T Kershey. Because the coordinates that we are going to deal with have a name, we call Kershey. Okay? T Kershey plus R. So you see, if a R must have been there, then these two changes would have been the same. So T Cauchy would have been equal to T. But F bar is not there at infinity. So this T Cauchy would be T at infinity. It will be different in the center, but let's see how that goes. Okay? So now we have to plug this coordinate change back in. Okay. It's an easy thing to do. Let me leave you to do this. Okay, it's an easy thing to do. Let me leave you to do this. And to check that what you get is ds squared is equal to dx mu, just flat space. Plus, minus, I'll have to check the sign with my notes in a minute, but let me, dr minus dt, the whole thing's, okay, it's all squared, so it doesn't matter. R by R naught to the power d minus. This is where this t is T Cauchy. Is this okay? You could plug in that coordinate thing into that formula and check the dx. Okay? This, when we were actually working on our first paper on the subject, we worked out this coordinate system ourselves. But then when I gave my first talk on the subject, there was a gravitational physicist who told me, why don't you just say you're working Cauchy? So that they realized we were working in a phase system. Okay. Now, this coordinate system has the following properties that I want. Two bits. Yes. Okay. I'm going to write this in the following way. I'm going to write my metric as ds squared is equal to, let me write g mu nu is equal to eta mu plus O mu by rho to the power d minus 3. Where in this particular case, O mu is equal to n mu minus u mu. Rho in this case is R by R naught. N is equal to d rho normalized. And u mu in this particular case is just minus 1, 0, 0, 0. Okay. This is the analog, slightly more complicated analog of the way when I was studying fluid gravity, I wrote the metric of the black brain in terms of some complicated u mu's and p mu mu's. You know what I mean? It was just a form of the metric such that if you replaced standard values for everything, you got back the simple looking answer. Okay? However, this form of the metric is going to be useful for what I'm going to be doing next. Is this clear? Questions or comments of any sort, algebraic, philosophical? Okay. Now I come to what is probably the most important statement in this course. Yes?
So what's the value of mu and
Mu and nu run over all indices of space-time. This is one form in space. In this case, we know what n mu and nu are, right? Because in this particular example, we know what this field, what this function rho is. It's R by R naught, as I represent. We know what the one form union is.
there is dx mu, and you have dv squared from the.
I'm so sorry, this is the R squared. This R. I'm really sorry about this. This is R.
Okay, but if that mu runs from 0 to d minus 1, what about the other? Oh, okay, you separate it.
This is some one form that corresponds to some k. It depends, what the value will be, it depends on what coordinates system you use. If you use Cartesian coordinates, it would be xi divided by square root of xi squared by xi squared. If you understand. Is this clear? Okay, great. Now I'm going to make what is, now I'm going to do what's probably the most important thing that I'm going to do in these lectures, which is this. So far I've just taken some well-known solution and written this in a complicated way. But the point about this is the following. Suppose I now replace rho not by this function, but rho can be any function. Okay? It's going to be a function that's smooth, varies over length scale. Okay? And perhaps to start with, let's restrict ourselves to something that obeys some isometry, such that the counting of powers of being. Moreover, I take u mu and replace it by, take it not to be this one-form field, but any smooth one-form field. Okay? N is the normal to rho, defined this way. But by the way, all norms, whenever I write norm here, let me be explicit about this. D rho dot d rho is eta mu nu, del mu rho, del mu rho. Okay? So inner products are always taken in the flat space metric. Rho will be thought of as a function living in flat space. U mu will be thought of as a one-form field living in flat space. What we're going to do is to take the data of fields in flat space to construct a new metric. Okay? So, we've got any function and any one-form field. And then we take this and plug it into Einstein's equations. Okay? For an arbitrary function, an arbitrary one-form field. Now, what? It's 0. It's just like 2. Okay. Now, what should we expect when we evaluate Einstein's equations of this metric in the neighborhood of the event horizon? In the neighborhood at the moment of the function of the surface rho is equal to 1. Okay, so I should say that just as in studying the actual black hole, everything was really interesting when rho was equal to 1. We always are not. Similarly, you will find everything in this metric is really interesting when rho is equal to 1. We see this as we go. Now suppose we, just as an algebraic exercise, we try to evaluate the Einstein's equations in the neighborhood of the surface rho equals 1. Okay? What should we expect to it? Well, Einstein's equations are two derivative. Each derivative will produce 1 over the distance scale of variation. In the neighborhood of the event horizon, we've just seen that the distance scale of variation is r naught by u. So a two derivative equation should produce, you would expect, something of order d squared by r naught squared. Okay, where r naught is some measure of length scale involved in this surface rho equals 1. This is correct. Okay? Now, so as leading order, Einstein's equation will evaluate order d squared. While it is some work to evaluate Einstein's equations term by term on this metric, it's easy to evaluate those terms that contributed order d squared. And you can just algebraically verify the following. That if the following two conditions work, del square 1 by rho by d minus 3 is equal to 0, and del dot u is equal to 0. I should have said u mu is any smooth one-form field that is always orthogonal to d rho. One-form fields that live on the submanifolds of constant rho. Okay? If these two conditions, these two things are both, like this is something order d, it comes with another explicit d. This is something order d which comes with another explicit d. Every contribution to Einstein's equations in this little region around rho equals 1, that is order d squared, the highest order that it couldn't, the highest order that appears, vanishes provided we impose these two conditions. Okay? There's something you can check algebraic. You can actually also argue logically. But it takes 10 minutes to make the arguments. Okay? So, now what we have, just one, you know. Okay, just one, really. Okay, so what we have? What we have is that we've now discovered that in the neighborhood of rho is equal to 1, Einstein's equations are obeyed to leading order, not just for this particular choice of the function rho and mu, but for any rho that satisfies del square 1 over rho to the power d minus 3 is equal to 0. Clearly that's satisfied by this, right? That's cooler. And for any rho and any u that satisfies del dot u is equal to 0. Clearly that's satisfied for this. That's obvious. Okay? Everything I said works in the neighborhood of the surface rho equals 1. But now the space-time can be divided into 3 regions. A small shell around the surface rho equals 1. Rho order 1 away from rho equals 1. And rho, order 1 larger than rho equals 1, rho order 1 less than rho equals 1. Let's first deal with rho order 1 larger than rho equals 1. In that case, what can we say about this metric? This metric is eta mu plus a number that's order 1 over a number that's order 1 to the power infinity. So that's 0. Same argument that we had earlier in this lecture. So we go away from rho equals 1 in one direction, we get back to flat space. Flat space may not be very well known, but it's an excellent solution to Einstein's equations. So flat space, solve Einstein's, so we've got a solution to Einstein's equations for rho, not on one side. On the other side, things go bad. When rho is smaller than 1, things start blowing up. However, I'm going to show you next time that rho equals 1 is an event horizon of this metric. So, if we solve the Einstein equations in this patch around rho equals 1 and everywhere outside it, we've solved Einstein's equations enough to predict the exterior of the event horizon, no matter what happens inside. Okay? So the punchline is that provided these two conditions are obtained, we have a starting point for perturbation theory of solutions to Einstein's equations. That's it. Thank you.